Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers, because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD, and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Hello, this is Richard Jacobs with the Finding Genius podcast, now part of the Finding Genius Foundation. My guest today is Albert-László Barabási. He goes by Laszlo, so that's what I'll call him. He's the Robert Gray Dodge Professor of Network Science at Northeastern University. We're going to talk about the unmapped chemical complexity of our diet, which will be very interesting. So, Laszlo, thank you for coming.
Richard, it's a pleasure talking to you.
Well, good. Tell me a bit about your background, and then how did you get an interest in the kind of research you're doing today?
Sure. So I define myself as a network scientist. I was originally trained as a physicist, but about 20 years ago, I started to use the tools of physics to start to understand complex networks. And these are anything from social networks of how we are connected to the people we know and we work with, all the way to communication network, internet, World Wide Web, cosmic networks, and so on. But among the many networks we explore within network science, I have had for many years a passion to understand the networks within our cells. That is the biochemical and the genetic networks that are within each of our cells, and the interactions between the components, between the genes and the biochemicals that really create life.
What do you mean? What are the networks inside of us within a particular cell or across cells? Or, from what I understand, there's many levels, the organs talking to each other, cells organized into organs and tissues, systems. And anyway, go ahead.
Richard, you're absolutely right. There are many, many different ways you can actually view a body as a network. Probably the most obvious to everyone is the brain, which is how the brain cells communicate with each other and lead to consciousness and thought and so on. Our journey is more elementary and more fundamental than that. So the Human Genome Project has provided us 20 years ago all the components of the cell, meaning they provided us the genome. Within the genome, we now know what are the proteins that the genome can create and what are the RNAs the genome can create. And through that, we also know what reactions a human or a bacterial genome can catalyze. Hence, what kind of chemical reactions could take place in the cell, which is really what drives the metabolism of the cell.
Is that metagenomics, estimating what the possibilities are based on the genes?
Metagenomics would be mostly applied to bacteria, right? And also the bacteria in your gut, the bacteria in the sea, in the soil, and so on. When it comes to humans, we have 20,000 genes, give and take a few, which each of them create one or often multiple proteins, and these proteins don't just float alone in the cell, but they assemble, they interact together, and they assemble little machineries. For example, the hemoglobin molecule in your blood is really assembled from 4 different proteins that attach together, and they're able to carry the oxygen and the carbon dioxide. And in the same way, every single machinery within our cell is really assembled from proteins. And these machineries are responsible from everything from copying the DNA, creating the RNA, as well as catalyzing every single chemical reaction. Because as you probably know, one of the special thing about life is that many of the reactions, much of the metabolic reactions that take place in our body would not take place naturally in a tube or something. You need to have the catalyzers, and those are our proteins. So when you put all of these together, on one end you have what we call the metabolism, which is a network of chemical reactions that how a sugar molecule is broken into components and turned into energy. And then you also have what we call protein interaction networks of how the proteins assemble and create the machineries. And we have one more class of networks we call regulatory network, which is telling us how you turn on and off different parts of the cell, different pathways and so on, and how the proteins interact with the genome to achieve that. So these are the networks within each of our cells, and these networks effectively govern what we call life.
Where does the governance come from? Do you believe it's self-governance within a network, or, what orchestrates the action of each network and the cooperation of the networks amongst the networks?
That's the beauty of it, right? It's evolution, right? So when you're born, you have one cell. You inherit one cell, which is a combination of the genome of your parents. And then it starts multiplying. And within the genome, the whole code is encoded, how these cells eventually becomes, brain cells or heart cells or skin cells, and what governs each of their behavior. So each cell has its own governance that is specific to what it does. A heart cell behaves somewhat differently from a skin cell, and that both of them behave drastically differently from a brain cell, whose main goal is effectively communication. And effectively all the food that we eat, right, and everything that we kind of consume is really consumed by this metabolic network within each of our cells.
Okay. So what kind of systems besides energy production govern the interaction of our bodies with the food we eat?
Well, you have to build everything. So there are reactions and systems who are responsible for building the cell wall. There are a bunch of reactions that turn on when the cell is multiplying during the duplication processes. There's a whole energy metabolism that is just simply creating ATP, and an insane amount of ATP needs to be created. I just read somewhere that not only that we have at any moment about a quarter of kilogram of ATP in our body, but on a daily basis, the metabolic network within our cells create roughly the same weight of ATP as our full body weight, which means that these
what is the energetic yield of a gram of ATP or a kilogram? Has anyone calculated that? If you want to compare it to a substance like crude oil, what would it look like?
It's a good question. This is the moment where I would turn to ChatGPT and work that out, right? I don't know top of my head the number, but it is an amazing kind of network that governs fine-tunes all the time the activity of each of our cells in a very differentiated fashion, because different cells have different roles within the body.
Okay. So I don't know, now that you're seeing that there are these networks, what do you do with that knowledge? Like, how does that help you in?
Good question.
Are you using this for disease?
Yeah.
How are you using this?
So one of the reasons we've been interested in these networks is because they are essential to understand how disease emerges in a human body. And one of the big discoveries we made about 50 years ago, that when you look at these very large and very complicated networks, then the components that are responsible for a particular disease, be that heart disease, be that asthma, be that metabolic problems, are not distributed randomly in the network, but there are certain network neighborhoods where they seem to be residing. And why is that important? Is because then if you want to cure that disease, you need to design a drug that hits in that particular neighborhood. Let me give an example that we can all better relate to. So if there's a traffic jam in downtown Boston, right? And that traffic jam is the result of closing down some main arteries downtown, so like Commonwealth Avenue, which is a major road saying downtown Boston. Then if you want to solve that problem, you're going to have to go in the vicinity where the road is closed and find pathways of how the cars can go around that. And it makes no sense to start solving the problem on the other part of the city, which could be also congestion because of this problem, but that's not where the problem relies. So fundamentally, by understanding the network, which is effectively getting a Google map of the cell, allows you to precisely identify what neighborhood you need to intervene to cure that particular disease. And this is what we call network medicine. And network medicine is around these days very hot. I have an appointment at Harvard Medical School. There we have a division of network medicine that has more than 200 researchers and medical doctors trying to apply network ideas to disease. There are tools actually that patients use without knowing these days that are network medicine based. For example, I founded a few years ago a company called Cypher, that is using network medicine tools to tell RA patients, that are rheumatoid arthritis patients, whether the particular drug will work for them or not, or what drug to choose actually as a treatment.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
So
how does it work? What's an ailment that relies on a particular network, and how would the medicine affect a network to eliminate the ailment or reduce the effects of it?
Wonderful. All diseases rely on networks. And actually, we tend to think that diseases are coming from the mutations. The mutations are really just kind of a component is broken. And the broken component typically leads downstream to some problems. For example, if a particular enzyme has a mutation and hence cannot properly catalyze a particular reaction, then downstream from that reaction, the products of that and the products of those products are not produced at the rate we need. And you may have a problem that apparently has nothing to do with that enzyme, but it has to do with the fact that the enzyme is not doing the job, and downstream 3 reactions later, we don't have enough chemicals that we need in the cell. So virtually any disease you think about it, you have to have a network perspective, because the genomics only gives you how the components are broken, but you need to understand how does that broken components impact spreads to other components in the cell and kind of lead to particular disease. And that's one of the reasons why virtually all the drugs that we have right now, and what I mean virtually means about 98% of the drugs, we did a study a few years ago, do not actually hit what we call the disease gene. That is the gene that we know is causing the disease, but they typically target proteins about 2 links away that is downstream from that problem. Because if you kind of target the disease gene, you cannot really often fix the problem, or almost never, but you can kind of go and cure the consequences of the problem downstream. So effectively, any disease you want to think about, it requires a network perspective, from cancer to metabolic diseases and so on. And this is a relatively recent understanding that has really emerged, say, in the last 15, 20 years. And now big pharma to small companies are using network ideas to really develop new drugs, identify new targets and new interventions within the cell.
Okay. I mean, is there, again, any examples specifically of drugs right now that affect a given network, and how? Are they looking for, would they amp up the amount of precursor for a final product? Sure. Are they attempting to block, a particular compound from being made, or reduce the, the side compounds? Like how does this work?
All of the above. Effectively, the way often I think about it is that what current medicine does is that it rarely fixes the source of the problem. What it does is that it goes downstream and gives you the chemical that you are missing. So a very good example is lactose intolerance, right? We're just going to give you the protein that you need to process effectively the milk, right? And virtually, yes, absolutely. And virtually all drugs do that in a more subtle way. And let me give you an example of how the RA product works, right? So there are several drugs for RA. One of them, the best known, is Humira, which is a very expensive drug. And only 30% to 40% of the patients respond to the drug. And why is that? Because the drug hits a certain neighborhood of the network, and those patients have the problem that leads to disease in a different network neighborhood. So, for example, what the Cypher Medicines tool does is that it takes a blood test and identifies where are the deformations or the changes in what we call expression patterns of a particular patient. And if it's in the right network neighborhood where, for example, Humira hits, then you say, go and take that. However, if it's in a different network neighborhood, then would say, this drug will not work for you. Choose another drug. And this is a wonderful example how you can use network medicine ideas to really tell the patients whether the drug will work or not. And it also tells us a little bit about the future. I would love to arrive to a moment where we never take a drug without first doing a test and knowing whether that drug will or will not work for me. How much time, how much money is wasted by trying different drugs for different patients. And in principle, network thinking and network diagnostics tools will allow us to shortcut that process and simply say, oh, you came out with that disease and there are 10 drugs available. Let me take a blood test or some other test and I tell you exactly what will work, and don't even try with the other. You will save lots of sufferings. You would get actually the patient much faster to a cure. You will save lots of money for healthcare. So everybody benefits. That's somewhere the future.
But how do you know which drug will work and which one won't? You'd have to understand, I guess, all the pathways and,
Yes, well, for all the drugs that are on the market, we know exactly where they hit. These days, no drug is actually approved without knowing where the targets is. And hence, we can see whether the changes you have in your cells that are specific to that particular disease that you may have are in the vicinity or not where the drug is hitting. If it's in a different neighborhood, that drug will likely not work. So that's the gist of the idea. And then on a practical level, we train what we call an AI classifier on this network neighborhood, and it learns from multiple patients what worked and what didn't, and it can make very accurate prediction about the success, whether the drug will work or will not. But the idea is always based on the network, that it's very simple, right? If Commonwealth Avenue is congested because there's an accident there, you will not solve the problem unless you act in the vicinity of where the accident is, right? And so if you go and bring your cleaning trucks in a totally different part of the neighborhood of the city, will not help the problem, right?
But why is this? This sounds like literal physical proximity.
Yes, it is. Network proximity, not physical proximity. Network proximity. So
what does that mean? Network proximity,
So think about it.
I don't know.
So if you have an accident on Fifth Avenue in New York, right? The cars will pile up many streets and many avenues up to that, right? And so the disease will not be limited to the location where the accident is. It will spread and affect a certain region of Manhattan because they're all running into this congestion moment where the accident was and they cannot go by, and hence they pile up. Similar things happen in the network, except that the network is not a square lattice any longer as it is in the Manhattan Green, but it's a very complicated network. And our job in network medicine is to map out this network and understand where do you want to hit. That is, where do you want to target your drug? And if you already have a drug, whether is the drug targeting in the right neighborhood for you, given the changes that you have in your cells when you are diagnosed with a particular disease.
Yeah, I just don't understand what you mean by physical proximity of the network. I mean, chemical reactions are going on. They may occur here, they may occur there, etc. So do you both need physical proximity and you need to be in the chain of reactants in order to affect it? Which are the levers you need to be able to interact with this network?
Richard, so I didn't say physical proximity. I said network proximity, and that's the right. So think about the social network, right? So if you want to kind of reach out to someone, the first thing you ask, hey, do I have any friends who may know that person and may be able to introduce me to him or her? And so it's no longer the physical proximity, right? You can be in LA and I can be in Boston, and we could find somebody, some common acquaintance who can actually make the introduction. And the same thing happens in the cell. The relevant parameter is not the physical proximity, but the network proximity. That is how the information and the matter is spreading on the network, because the chemical networks are effectively, you can think of as fluxes of chemicals flowing through from one reaction to the other one, and also fluxes of information going through in what we call the signaling network and so on. So you have to change your mindset, and that's what network medicine does for you. And don't think of physical proximity. think of network proximity and think of network effects. And the reason why this is hard to do is because while Manhattan and the Boston map is two-dimensional, a network is inherently infinite dimensional object because you could be connected to any one principle, any other node, and hence you need the tools of network science to effectively achieve that. And that's why we have network science, is to provide you the tools, even in such a non-trivial environment as the cell, where there are hundreds of chemical reactions taking place any moment, creating hundreds of billions of chemicals in parallel. And the proximity, physical proximity is a factor, but the real factor is really the networks, the chemical networks that facilitate all the processes within the cell.
Sure. So what kind of networks are you focused in on and studying, and what kind of drugs or for what conditions?
Sure. I mean, we are right now focusing on RA. We're also starting a new project, actually, trying to understand using network principles, aging processes. But we also have in the lab a big project that we call the Foodle project that is asking what's the role of the food in any of these processes that I just described. And I know originally we meant to talk about food. So probably it's a good moment for us to say, what does food have to do with any of this?
Right.
And the reason why food became interesting for us is because when we map these networks out, we all rely on genomics. But we know that genomic effects are give limited predictive power for disease. So for example, when you look at heart disease, if I collect all the genomic markers leading to heart disease for an individual, I may be able to predict with 20% accuracy that he or she will have heart disease. Or the other way to put it, about 20% of disease occurrences in heart disease are due to genomic effects. And the question is, where is the rest? And the answer always, the rest is environment. And the environment is stress, it's sleep, it's exercise. But the biggest gorilla in the room is food. And because at the end of the day, every day we get ounce of food into our body that in some ways spreads throughout the cells and provides them the energy and all vitamins and everything else the cell requires to function. So about kind of 7 or 8 years ago, we said, now we got pretty far with this network medicine picture, but how do we integrate the role of the food when we know that food has such a defining effect on health? And we thought, oh, that's easy because we know what's in the food. What are the chemicals in the food? That's what nutrition does. So we will just see how these chemicals interact with the components of the cell, be that metabolic components or be the proteins or regulatory processes and so on. And that's really when the main surprise arrived to us, because we were under the impression that we know what's in the food. And indeed, nutrition science does actually catalog what we call nutritional components, which is about 150 components that includes sugars, that includes amino acids, includes different types of fats, as well as several vitamins. And the reason why nutrition science focuses on these nutritional components and the vitamins is because these are absolutely necessary for us to survive. They are the fuel for the cell's existence. Without that, you don't stay alive because you need energy and you need vitamins. What was interesting when we started looking into that is realized that there are many, many more chemicals that are not nutritional components. And when we started this journey about 5-7 years ago, our first evidence was for about 20,000 components, 20,000 chemicals that are in the food that are not nutritional components. That number currently in my lab is about 135,000. So we have 135,000 chemicals that we digest through the food and eventually somehow get in our cells, and we don't know what they are, and they're not cataloged in any database. You will not be able to find out what's in lettuce or what's in the beef. And let me give a specific example. So if you take garlic has about 67 nutritional components, and these are cataloged by the USDA databases, both in the US as well in Europe and in many other countries. However, garlic has more than 2,000 different chemicals that are not nutritional components. However, many of them have direct impact on our health. One of them is allicin, which is providing the smell of garlic, and it's also providing many of the health benefits of eating garlic. As you know, garlic is a staple food of the Mediterranean diet, and effectively allicin is the active ingredient that is responsible for many of the positive benefits of garlic within that diet. Allicin is not a nutritional component. It's not cataloged, it's not measured in the different type of foods. So that led to the concept of what we call today the dark matter of nutrition, that there's an exceptionally large number of chemicals that reach us through our food that are non-nutritional, but they are very, very important for health, that are not cataloged, yet they play an essential role in keeping us alive.
All right. So how is this going to correlate all these compounds and factors within a given food? I mean, there's so many. So how does that affect the network? How do you test each food in isolation or in combination? What do you do?
Richard, that's a very good question. So let me tell you a story about polyphenols, right? Polyphenols, we know they're good for us. And one of the reasons we are being asked to eat lots of fruits and vegetables is because fruits and vegetables are rich in polyphenols. There are about 5,000 different polyphenols that come in the food, and polyphenols are not nutritional components, meaning that when it gets into your bloodstream, our metabolic processes do not process it. So they don't consume it. Our body doesn't consume polyphenols, yet they get into our cells. What do? They bind to proteins and they activate the activity of the proteins. They let them do certain things more effectively. In other cases, they block their ability to do things. And they also have what we call antioxidant activity. So what's amazing about the polyphenols, as I said, is that they're not metabolic. Metabolism does not at all see them, but yet they have an exceptionally positive health effect on us by turning on and off different processes within the cell. So how does network medicine and polyphenols come together? Well, we know what proteins the specific polyphenols bind to, and we were able to show that by binding those proteins, they actually modulate processes that are good for us. Let me take a very well-known example, which is green tea. As you know, green tea consumption is believed to be very healthy, and it has impact on many diseases, like particularly metabolic diseases and so on. And the active ingredient of green tea is a molecule called EGCG, which is a polyphenol, and it achieves that activity by binding to cellular proteins within our cell. And when you look what proteins it binds to, it turns out that it binds to lots of proteins in the vicinity of what we call metabolic syndrome, different metabolic diseases, as well as several other diseases. So just by looking at what proteins can the ECGC molecule in the green tea bind to, we can tell you what diseases will it affect, and we can make very specific prediction how it affects. So this is an example of a well-known kind of chemical, but we're using the same ideas and the tools of network medicine. We're now able to take any molecule that comes in our food and reaches our body, and we can tell them where they bind and then what diseases could they affect. Why is this important? It is important because this could lead us to food-based therapies. That is, on one end, we would understand what are the food-based molecules that affect in a positive or in a negative way a particular disease. Right. And if we identify those, then we may be able to even develop not only just change your eating pattern to enhance or to kind of like lower the symptoms of disease, but we may be able to even identify new drugs by kind of turbocharging some of these food chemicals and turning them effectively into a drug. So this understanding of merging the dark matter of nutrition with the network medicine principles effectively activates food as drug and opens up many perspectives for us of how to treat diseases through naturally occurring chemicals.
Right, but if food is not patentable, then, that's why it seems like, medicine is just geared towards drugs. So it's isolating one component and then using that as a drug. But foods, they have many, many other compounds that we may or may not understand their effects. So, the ECGC you talked about, how is that potentiated or affected by the other compounds in the green tea?
This is wonderful questions, right? And this is exactly some of the scientific challenges that we are trying to understand as we speak. And you are right, food is not patentable. But are we really after patents, or are we really after treatments and lowering suffering of humans? So if you live in the US, the only way we can...
Well, supposedly we're after helping people, but
there you go. There you go. So you're right. Absolutely. You did put your finger on the problem that if you create a food-based drug or a food-based treatment, there may be no incentives to bringing it to the market the way that you would actually have if you have a new drug that could make you billions of dollars. But, I'm a scientist and I'm an idealist. So I would like to look for treatments primary and worry about the economic setup of how to bring it to the patients after that. But the questions you ask are particularly, how do these effects coexist? This is a wonderful question, right? And some of the questions, this is exactly what we are researching as we speak in the lab, that none of these chemicals in the food come alone, and hence how do they influence each other? And it's well known, there are well-known influences in that sense. Even what we call food and drug interactions, there are certain foods and drugs that don't go at all well together. That is, the drug loses its effectiveness in the presence of the food. And also in the food, at the same time, you have chemicals that kind of make the disease worse and others that make it actually better. Let me give a very specific example. We use these tools to identify all the chemicals that could affect flares in rheumatoid arthritis. So like the pain actually for patients. And what the machinery or the network medicine tools provided eventually is about 30 chemicals that we predicted that could affect RA. And then we sent it to the lab and we said, go ahead and test the role of these chemicals and their impact on inflammation, which is because RA is an autoinflammatory disease. And short of a few, first of all, the lab fully confirmed that all of these molecules are affecting inflammation. It also told us that 5 of them are anti-inflammatory and about roughly 20-something of them were pro-inflammatory. Why is this important? Because now we know that these kind of 30 chemicals are involved in how the patients perceive RA and the pain and so on. And on one end, the easiest one is to say, we'll advise you to eat food that has less of the pro-inflammatory chemicals and more of the anti-inflammatory. And step 2 is to actually go ahead and create a granola bar and other food where these chemicals, the good chemicals, are enriched and you don't have the bad chemicals. And this is exactly what we did. And we are hoping to go on clinical trial with this particular product. But so in a way, this gives you very specific information for specific diseases of not only what foods, but what chemicals in the food affect that. And then you can step back and at the first approximation, you can change your diet. But then down the line, you can also create treatments by kind of creating foods that are enriched in the good molecules and they're depleted of the bad one.
Okay. So your focus is on rheumatoid arthritis. Are you looking at it from the food angle for rheumatoid arthritis, or what's your main focus right now in the research?
So it's interesting. We are agnostic to disease in the sense that the tool set is applicable to any disease from RA to cancer to neurological diseases. When we focus on a particular disease, it's typically because we have a partner, either a company or a spin-off or something that has made the case that ideas could be taken to market and could actually help the patients. Because it's not enough for us to come up with wonderful discoveries that we publish. I'm also looking always for a pathway. How can we get that one to the patient? And for that, you have to put this into practice. That is, either you have to work with a company who has the ability to do that, or you have to create a spin-off of your own. So in the case of RA, we do have a spin-off, and that's Cipher Medicine, but that's on the diagnostics. And we had another spin-off that was called Naring that was purchased by some other company who focused on the food and RA. And right now, what I'm most excited in the lab, and we don't have results, I cannot reveal new stuff because we're at the early stages of the process, but how could we actually use the tools of network medicine as well as the tools of foodome, that is the diet changes, to think about aging. That is to kind of the processes that affect aging and particularly healthy longevity. So this is something very new in my lab. We started about a year ago, and now we are heavily applying these tools to the networks within the cell that affect healthy longevity.
Okay. Well, very good. László, where is the best place for people to find out more about your work? It sounds like, again, a whole new area, a lot to know for even people to kind of get the basics of it. So how can they start to learn more and dip their toe in? Where can they go?
Absolutely. So go to the barabashilab.com and click on the Science tab. And within our publications, you will find virtually everything that I told you about. That's kind of a good place to start. You found us through this paper that was called The Unmapped Chemical Complexity of Our Diet, which is in Nature Food, and it's available on the website. So that would be probably the best place to start. And if you are interested and you want to go deeper, come and get in touch with us, and we can see if we can help you with the process that you are in.
Very good. Well, László, thank you so much for coming on the podcast. I appreciate it.
Richard, it's a pleasure talking to you.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.